In the last unit, we looked a lot at modeling the friction factor and other tasks. The next challenge we need in order to continue that process is to be able to measure the flow rate through the system. Now, many methods exist for measuring flow rate, and the choice of which method we're going to use depends on a range of factors. Things like the cost, its accuracy, the range of conditions that can be measured. For some, if it has a narrow range, you might have to buy more than one instrument. How easy they are to use and how long they last in service are all important. You need to balance these choices. You essentially get what you pay for. Low-cost instruments tend to have shortcomings, either in accuracy, range, or service life. The simplest type of flow meter is to just directly measure how much fluid is moved. We call these positive displacement meters. A rotating disc or some kind of piston is used to measure how many pieces of volume move past the meter. So a particular amount of volume can fit in the positive displacement flow meter, and the number of rotations times that volume gives you the total volume that's flowed through. Examples of positive displacement meters would be household water or natural gas meters or gasoline pumps. So then these types of flow meters are calibrated for a desired output, which is the cost of the fluid. Now these are some of the simplest flow meters, but their accuracy is not always very high, so they don't work for every application. We could also try to measure the velocity distribution across the flow channel. We could use something like a pitot tube or a pitot-static tube to measure the velocity at various points and then integrate to find the average. However, this requires that we have access to the flow field through the wall of the flow channel. It also requires a long time to make these various measurements, so the response time of this measurement method is very slow. And if the streamlines are curved, we have a lot of uncertainty in the quality of the results from these types of measurements. So, we've come up with a wide range of applications to find different values for flow rates. The simplest of these methods is called the restriction flow meter. Basically, you have a reduction in area that causes the fluid to accelerate. You measure the pressure change, and you use the pressure change to infer the flow rate through Euler's equation in order to measure that. Now, there are various types, but all of them use essentially the same equation, which is the one given here. The constant in this equation is determined from experimental calibration, and they're typically provided with a product when it's delivered from the factory. The selection of which type you want to use depends on cost, operating cost, and so on. Now, the most basic is the orifice plate. The orifice plate is basically a thin metal plate with a hole in it that you install inside a pipe. It's a very simple geometry. It has very low initial cost because it's easy to make. It's very easy to use. However, there's some complications. The first one is it's possible to measure the pressure at various locations. However, changing those locations changes the calibration constant. So it's very important to be careful to match your measurement conditions to the conditions under which the orifice plate was calibrated. They also tend to have very high head loss, so the operational costs or the additional power that you have to provide to the system to overcome that head loss is high. There's also an issue with dirt building up on the upstream side because you have that sort of stagnation region on the front side of the plate. Flow nozzles can also be used. The equation is actually identical to orifice plates. However, the discharge coefficient is calibrated a little bit differently. One of the major features about flow nozzles is it's easier to find the location where the velocity is the highest, what's called the vena contracta. So it's easier to determine where you should be measuring the pressure. These are more expensive to make than orifice plates because the nozzle has to be made, but the head loss is smaller, so the operating costs are smaller. So there's a little bit of a trade-off there. Venturi meters are actually cast and very precisely machined to have smooth sides without any sharp edges. Because of this, they tend to be pretty heavy and very bulky and expensive. However, because the inside of the Venturi meter is very precisely machined, they tend to have very low head loss, so the operating costs are low. They also tend to be self-cleaning because they have very smooth contours, so any dirt is just carried along with the flow. The discharge coefficients for Venturi meters range from 0.98 to 0.995. So 0.99 is usually a good approximation for most conditions involving incompressible flows. Now, manufacturer-supplied calibrations can further improve the accuracy. The problem with most of these restriction flow meters is that the range of flow rates that can be measured is fairly small. The range is typically around 4 to 1, which means that the maximum measured flow rate is only about 4 times the minimum measurable flow rate. These types of flow meters can also be used for compressible flows. However, the equation has to be modified to account for that compressibility. So we can't use the same equation and the same discharge constant for compressible flows as we have for incompressible flows. Now, there are a lot of other types of flow meters. A very common one is called a laminar flow element, and it makes use of Poiseuille's equation for laminar flow. The individual elements have very small diameter, so the Reynolds number inside each one of these tiny elements is very small, and so the flow becomes laminar, hence the laminar flow element. From Poiseuille's equation, pressure drops linearly for laminar flow. So we can measure the pressure drop across a single tube and use Poiseuille's equation to calculate the flow rate through that tube, and then multiply that by the number of tubes in the meter. So the resolution for this meter is very good over a wide range of flow rates, in fact a 10 to 1 range. So the maximum flow rate this can measure is about 10 times the minimum. It's similar in initial cost to a Venturi meter, but because it doesn't use as much material, it's lighter and it's quite a bit smaller. The trade-off is that it has a larger pressure drop because of the laminar flow and the very large surface area here. The other complication is that the pressure drop depends on the relationship between pressure drop and flow rate depends on viscosity. So it's very important to have an accurate temperature measurement when you're using this type of instrument. But as we said earlier, it has a linear output. The flow rate is a linear function of pressure drop, which helps expand its range because other flow meters tend to be nonlinear. For instance, in a restriction flow meter, pressure drop is a function of velocity squared or flow rate squared rather than a linear function. So that limits its usefulness compared to the laminar flow element. Ultrasonic flow meters are another very interesting flow measurement method. The idea here is to measure the shift in sound waves. For clean liquids without a lot of contaminants, you can actually use the propagation time of the ultrasonic sound wave to measure the flow speed. That's called a time of flight flow meter. If you have a liquid that has a lot of particles in it, you can use a Doppler flow meter, where you measure the change in the frequency of the sound waves as it reflects off of the moving particle. What's really convenient about ultrasonic flow meters is they can be just clamped on the outside of an existing pipe, so you can add one to a system without having to make extensive modifications. Float meters are a very basic flow measurement device. You have a weight with a particularly designed shape inside of a chamber where the area slowly gets bigger and bigger as you move up. And so what happens is, as the area gets bigger and bigger, the velocity gets smaller and smaller. And the location where the float sits is at the same velocity. So if you increase the flow rate, the point where that velocity occurs is going to be higher, and the float meter is going to move up until the drag force counteracts gravity. These are also called rotometers, or several other different types of trade names, and you measure the volume flow rate directly off of these rotometers. Turbine flow meters are interesting because they contain a freely rotating impeller. So as the gas moves through the flow meter, it spins this impeller, and the rotation rate is measured, and it's actually linear over a pretty wide range of flow rates. What's really convenient about this type of device is that you don't need to mechanically measure the rotation rate. You can use magnetic fields to measure the rotation rate. And if you do that, you can design one of these such that there are no penetrations from the outside to the inside. so it's completely sealed, and you don't have to worry about any rubber seals or gaskets or anything like that. This is really good for measuring toxic or corrosive fluids, or basically any time you're really concerned about any kind of leakage. The vortex flow meter takes advantage of the von Karman vortex streak, the idea that bluff bodies create these vortices that break off on alternating sides. This creates an oscillating sideways force which we can measure with a force sensor, and the frequency of these vortices is proportional to Reynolds number. Now, calibration is required because there's a velocity profile in these types of flows, so you have to calibrate the frequency to the Reynolds number and the Reynolds number to the average velocity. However, they do have a very wide range, a 20-to-1 range of flow conditions that can be measured. Electromagnetic flow meters use the principle of magnetic induction. It requires a conductive liquid, and then that liquid flows through an applied magnetic field, and this induces an electrical voltage. However, the flow speed has to be greater than about 0.3 meters per second in order to use this type of technology. We can also look at measuring local behavior of a flow using things like thermal anemometers. Thermal anemometers use a hot wire or hot film element that's electrically heated, and you measure the input heat rate needed to maintain a particular temperature. Next semester in heat transfer, we'll learn how heat transfer is related to flow speed. So it does require some calibration to relate the input power to the flow speed. The benefit here is that the sensors are very small. They can be as little as 0.002 millimeters in diameter and 0.1 millimeters in length, which means they have a very fast response time. And as you can see in the picture, you can actually use 3 different hot wire elements to measure the velocity in 3 different directions. So you can measure the 3D components of the velocity on very small timescales, which is good for measuring turbulence parameters. We can also look at things like laser Doppler anemometry, or LDA. Here we have lasers focused on a small volume, and the 2 lasers have slightly different frequencies. So where the lasers cross, it creates an interference pattern with light and dark bands. The laser light is then scattered from small seed particles added to the flow, and that reflected light is measured by a sensor. As the particle passes through the interference bands, it alternately reflects light and then does not, and then reflects light again and does not. So you can, if you know the frequencies, then you can calculate the distance between the light fringes, and you can measure the time it takes for the particle to reflect light from adjacent fringes. So now you have a distance and time, so you can calculate velocity directly. That means there's no need to calibrate this instrument. It also doesn't depend on temperature or density or any of these other parameters. The downside to this is that the optics are very expensive and very delicate. It's very easy to misalign these sensors due to vibration or some other issue and reduce the quality of your measurement.